Hello students, today we are going to learn the new chapter thermodynamics. In the previous chapter, we have studied about the thermal properties of matter. Actually, in this chapter, we shall study the law that governs the thermal energy, and we shall study the process where the work is converted into heat and the vice versa. Now, we are going to learn the subtopics of thermodynamics and the thermal equilibrium, thermodynamics equilibrium, and the Zeroth Law of Thermodynamics, heat and work, the internal energy, and the indicator diagram. One by one, elaborately we will study, children. Yes, students, thermodynamics. See, thermodynamics is the branch of physics, deals with the concept of heat, temperature, and interconversion of the heat and other form of energy. So, thermodynamic system, which means we can say that a large number of particles which is present in the system, that is having a certain value of pressure, volume, and the temperature, right? Now, about the surroundings of the system, that has to be everything outside the system that can have a direct effect of the system, that we can call it as surroundings. And the thermodynamic variables. See, the thermodynamic variables such as they have given us a pressure, volume, and the temperature that will help the system to study the behavior of the thermodynamic system. So that variables we can call it as thermodynamic variables. Yes, thermodynamics. So the thermodynamics for the condition we can say that the two system, if suppose the two system there are said to be thermal equilibrium, then we can say it has to be, the two system has to be same temperature, right? See the diagram, children. Now you can consider the two gases A and B that contain in two different vessels which is separated by a diathermic wall. That wall is a diathermic wall that we can say it's a conducting wall which allows the heat to flow through it. So that is only this wall which allows the heat flow through the next side. So the gases A and B which is contained in a different vessels, right? Now the pressure and the volume of the gases PA and VA and PB and VB for the two gases accordingly for that A and B. So due to the course of time, the pressure and the volume, that variables of two gases will change simultaneously until it will take the place of the same temperature. It may be, we can say that is, it has to be thermally equal, right? So now there is no more flow of heat will be occurring at the time. We can say this two system attains the equal temperature. At that time it is thermally equilibrium, right? Thermally, that both liquids are getting equilibrium, right? Yes, thermodynamic equilibrium. If suppose the system is said to be a thermodynamic equilibrium, we can say that the microscopic variables which is describing the thermodynamic state of the system that do not change with time, right? That we can call it as thermodynamic equilibrium system. And we have mechanical equilibrium, thermal equilibrium, and the chemical equilibrium. See, the mechanical equilibrium, we can say that there is no unbalanced force is in its interior or between the system and the surroundings. That we can call mechanical equilibrium. The next one is the thermal equilibrium, which is nothing but all parts of the system and the surroundings are in the same temperature. If suppose the temperature is same, this is the thermally equilibrium. And the chemical equilibrium, the system that does not undergo any spontaneous change in the internal structure due to the chemical reaction. So that we can call it as a chemical equilibrium. Yes, students. Next one is Zeroth Law of Thermodynamics. If suppose two systems, that is A and B, that are separated, that means separately we kept in a thermally equilibrium system, with the third system which you are seeing on the screen, the diagram shows that A and B which is separated with the system, but it is a equilibrium, thermally equilibrium system. With the third system we kept. See, now we can say that A and B are also in the thermal equilibrium with each other. Right. See the diagram, students. See, now this two systems A and B which are separated by an adiabatic wall. The adiabatic wall, which means the heat does not flow through one system to another. A and B will not conducting wall. It is not like a conducting wall. So it is an adiabatic wall, right? So we are kept through the adiabatic wall. They are separated from the system C by a diathermic wall. See, diathermic wall, which means we can say that the heat can flow through that. From C, the heat can flow through that. That is the diathermic wall. Now, the systems A and C, B and C will reach thermal equilibrium separately. If adiabatic wall between A and B, if suppose we removed, that means there will be no exchange of heat, showing that A and B are already in equally thermalibrium equal state, right? So here we can say about the concept of temperature through the zeroth law. See, the zeroth law of thermodynamics, which states that the temperature is a physical quantity which has the same value for all systems which are in thermally equilibrium or a thermal equilibrium with each other, right? Now, internal energy. So the internal energy, which means the sum of molecular kinetic and the potential energies in the frame of reference, which is relative to which the center of mass of the system, it should be at rest, right? So, the molecules of a real gas that suppose exerts mutual force of attraction on one another, then they possess the intermolecular potential energy. So, the intermolecular potential energy of a real gas is a function of its volume, right? Now, you have to know about the internal energy of an ideal gas is purely kinetic in nature. We can say for that the internal energy for the ideal gas, there is no molecular force of attraction. There is no molecular force of attraction. So, it does not have the intermolecular of the potential energy which is there. So, we can say the internal energy of an ideal gas is wholly kinetic in nature and it depends on the temperature. It depends on purely the temperature. Right. So, these are the conditions which is for the internal energy of an ideal gas is purely kinetic in nature. That there is no molecular forces of attraction between them. Because of that, it does not have any intermolecular potential energy between the molecules. It is depending on, because of that, the internal energy of an ideal gas is purely depending on the temperature, right? Next one is heat and work, which has two distinct mode of energy. See the diagram, students. See, you may see that a fixed mass of the gas in a cylinder which is provided a movable piston. The internal energy that can be increased in two ways in that system. First one is, if suppose you place the cylinder over a hot body, the heat energy will flow from the hot body to the gas due to the temperature difference. Because of the temperature difference, the heat energy will flow through that. So, we can say that is the internal energy that can be increased. So another way, we can say the work has to be done on the gas. How? You may push the piston down by raising the weight which is attached to it. That time the work will done on the gas. That time also the internal energy will increase. Right. So by these two ways, we can increase the internal energy, and we can prove that the heat and the work that has two distinct modes of energy. Right. So now we are going to see the differences between heat and work. See, the heat, we can say that the mode of energy which is transferred, the temperature differences between the system and the surroundings. Whereas we can say the work is the system, that is the mode of energy which is transferred, brought about by means that do not involve any temperature differences, right? And the heat which produces random motion. That we can say that is the heat is the mode of transfer of energy that only produces the random motion. The work, it is organized motion. The motion is always organized in the work, right? So now this is indicator diagram. Through this discussion, we are going to know about what is indicator diagram and what is the importance of this, right? See, the graphical representation that of the state of the system with help of two thermodynamical variables, which we can call it as the indicator diagram of the system. See, the graph between pressure and the volume, you may have observed through this diagram. This is PV diagram. We can call it as, this is a PV diagram. So this PV diagram, the graphical representation between the pressure and the volume. Now, the two different diagram which is on the screen, right? So the PV diagrams of two systems will help to undergoing the expansion and the compressions respectively. The first diagram will show us the expansion of how the indicator diagram shows, and the second diagram which gives the relation between how the pressure and the volume will show the graphical representation of the compression of a material. So what is the importance of the PV diagram actually? See, the area under the PV diagram is numerically equal to the work done by a system or on the system, right? Yes, students. So far we have learnt about thermodynamics, thermal equilibrium, thermodynamics equilibrium, and the zeroth law of thermodynamics. And what is the relation between the heat and work, internal energy conversion, and the indicator diagram, graphical representation. All those things elaborately we have studied. Hope you people have understood. Thank you, students.